Frank, you're on.
Good morning, everyone. We will be beginning presentation here in just a few minutes, promptly at 9:15. So just giving everybody a few minutes to log on. So thank you for joining, and we'll start shortly. Presentation here promptly at 9:15. We'll give everyone just a couple more minutes as some are still logging in, come in. So if you have any questions during the presentation, please enter them into the chat, and we will have a time for Q&A at the end of the presentation. So thank you again for being here this morning, and we'll start here shortly. Good morning, everyone. Thank you for being here and being present for our first presentation of the day. My name is Frank Gordon. I'm with the National Ready Mix Concrete Association. I am an architect by education and have been in the construction industry for over 30 years. This morning, we're going to be talking to you about the case for building resilient, high-performance schools. Now, a little bit of housekeeping up front for each of you, as some are still logging on. Everyone will come in muted, as we typically do in a lot of these Zoom webinars. And if you have a question, and we encourage any questions that you might have, please enter them into the chat box. We will have a time of Q&A following the end of the presentation. So please, if anything comes up, and if it's a specific slide, don't hesitate to reference to that, but we'll have a time of Q&A at the end of the presentation. But thank you for being here this morning, and we'll go ahead and get started. So the case for building resilient, high-performance schools. As most of you are aware, with AIA presentations, this is a certified presentation by the AIA. We have some basic learning objectives that we're going to be trying to accomplish today. One is to recognize building envelope systems that create durable and sustainable high-performance buildings, specifically using ICF or insulated concrete forms. Another is to identify design assistance tools to evaluate, design, and specify resilient high-performance concrete buildings. Another is to describe why resilient, strong design is necessary to create sustainable educational facilities that help teach students about their advantages. And lastly, we'll be looking at identifying resilient, strong concrete solutions that create safe and secure high-performance projects. I want to take just a quick little second to thank some of our sponsors at the NRMCA, the least of which is not the Carolina Ready Mix Concrete Association, who is our partner in the Carolinas. And I'll be sharing some of that contact information also at the end of the presentation. But if it wasn't for these sponsors, we would not be able to do the online learning opportunities that we've had in conjunction with A4LE and the opportunity that they've afforded us here today. So thank you for allowing us to be here, and thank you for the time to present. So we're just going to jump in right off the bat with the definition of what resilient is. As you can see the definition on the screen, a very simple definition of resilient is the ability to withstand or recover quickly from difficult conditions. It's also the capacity of a dynamic system to adapt, prepare, absorb, and recover from adverse events, whether they are natural or man-made, that threaten the function, survival, or future development of that system. Now, some synonyms that we would associate with resilient would be strong, tough, hardy, quick to recover, buoyant, or irrepressible. Now, with respect to habitat and communities, resiliency is this act of maintaining functioning livable conditions at all levels and scales of a development. Now, resilient design isn't the same as sustainable design, but they do have a lot in common. And according to RDI, it's the intentional design of buildings, landscapes, communities, and regions in order to respond to natural and man-made disasters and events, as well as long-term fluctuations resulting from climate change. Resilient design is also in many ways an expansion of the definition of sustainable design. For designers and builders, it's another complex layer in a process that already is becoming complicated. But for owners, it's an added cost, but it's also becoming a necessary investment in today's world. In the past decades, the rise in natural disasters have left the population more vulnerable. Building codes are usually cautious and slow to escalate in their stringency, but that doesn't mean that design and construction has to always align with the minimum allowed by code. So as you can see in the graphs and the diagram on the screen, this is data that has been gathered from NOAA, the National Oceanic Atmospheric Administration. And you can see that the increase in climatic events and billion-dollar disaster events has been dramatically increasing over the past decade. You can see the different types of events in the diagram that's on the left-hand side of your screen, and you can see how they are identified, whether it's drought, flooding, freeze, severe storm, cyclone, wildfires, or winter storms. But you can also see that the trend line of the cost of these events has been definitely increasing over the past couple decades. So what are some steps to resiliency and sustainability that we can look at? First of all, we have to look at adopting updated building codes. As I mentioned before, the building codes are typically slow in their ability to respond and to be able to adapt to what's going on in the climate. Also, you have adopting high performance building standards. As we have seen through the onset of LEED, through Living Building Challenge and other programs that are out there, we have the ability to up the standard. In other words, set the bar higher for what we're shooting for in the way that our buildings respond to these type of events. Also, to incentivize disaster resilient construction. If you're going to ask a contractor or an architect to design to a higher standard than what they are typically used to, then that's something that has to be looked at in the way that they are compensated for what they do. But we also, something that we can do immediately or do right now is we can be building with more robust materials and building systems that help us achieve these goals that we're trying to attain through resiliency and sustainability. Now, some resilient and energy saving strategies that are already available in the market and already we have seen as requirements in a lot of the markets that we're working in. Number one is right off the bat, ICC 500 compliance, especially if you are in a coastal area or an area that is prone to storms. You are familiar with what this requirement is and how you're designing essentially for a storm shelter. Also, multifunction and adaptive use. Building facilities that address multiple community needs for greater effectiveness, so that you're not just building facility for one use, you're building something that can be a multiple use facility for the community around it. Also, we look at integrated energy efficient systems. Geothermal HVAC, LED lighting packages, Energy Star rated equipment, energy management software, and building controls. These are all part of a strategy that help in building resiliently and energy saving. And also net zero ready. This is something we're going to be talking about today. You're going to be hearing more about it this afternoon as well. And it's something that has been coming into the building and design community over the last 10 to 15 years, in that creating and building facilities that have the opportunity to generate their own power, supplementing their own power usage, and possibly even creating more power than they use. And then high performance envelopes, airtight, super insulated exterior shells that are utilizing thermal mass and low energy bridging, which allow them to operate very effectively and efficiently in the market. So, because we are the National Ready Mix Concrete Association and the Carolinas Concrete Association, Ready Mix Concrete Association, we're going to be talking to you a lot about concrete today. Now, we're going to be talking a lot about those systems that we referenced just a second ago. But one thing that I want to point out that you need to be aware of is that without an effective insulated shell as a foundation and as a beginning to all these facilities, it's hard to achieve some of the performance that you're looking for in a resilient and sustainable structure. It's not impossible, but it definitely becomes a lot more expensive and a lot more complicated. So just as a quick refresher, some of the types of concrete frames that are out on the market, you have a conventional cast in place frame where your columns and your beams and your floor are all formed up and the concrete is poured in place. You also have a precast frame component where beams and columns are already cast in place, and then those elements are used and put together to assemble a structure of a facility or a building. You also have tilt walls for exterior construction. We see a lot more of this in warehouses and large facilities, but we're also starting to see some schools that are being built out of tilt wall because they are very fast. They can allow you to get into a facility very quickly. And if you have the right contractor that can work in that system, it can definitely be a time gain in your construction schedule and can potentially also save you money. But we also are going to be looking at today insulated concrete forms, and that's going to be at the heart of the discussion that we have today. And a lot of people think insulated concrete forms or concrete buildings are just meant for certain types of structures, and they're typically thought of as being cold or being very simple and simplistic in the way that they're put together. But the truth is, all of the types of structures that you see listed at the bottom of your screen, lodging, healthcare, offices, commercial realty, public safety, multifamily housing, college dormitories, religious worship centers, prisons, industrial centers, data centers. These are all facilities that are being built with concrete structures and being built out of insulated concrete forms. The one that we're going to be talking about, of course, today the most is going to be educational. So let me give you a brief history of ICF, because a lot of people think that ICF is a fairly new technology. The truth is that ICF has been around for the better part of going on over 70 years now. So it got its start in 1937, Belgium. It was a product called Durasol. And if you actually do a search now on the internet for Durasol, you'll find that there is a company in England that is manufacturing an ICF, an insulated concrete form, that is still called Durasol. It's not the ICF that we typically see here in the North American continent, because their exterior shell and panels are typically made from different material than EPS or expanded polystyrene. But they are a company that makes ICF still, and they are still in business. Post-World War II, Europe was where it really started to catch on. You had a lot of rubble, a lot of mass and ground material that was left over from the war. And so they started taking that material, grinding it up, putting it in forms, and then using those forms to pour concrete in. In 1959, it was introduced into 13 different countries in the European nations, and it was used rapidly to help reduce costs for rebuilding from World War II. In 1966, a gentleman named Grigori filed the first patent in Canada to have ICF manufactured, and the exterior shell was made out of polystyrene. And then right after that, in 1967-68, was the United States patents were filed for the same thing. So in the 1970s and the 1980s, we saw substantial growth in the industry. It was still a fledgling industry at that point, but we saw a lot of basements. We saw a lot of facilities that were in extreme climates, especially climates up north, that were being built out of ICF. In the 1990s, the industry grew to a point that there was over 30 different manufacturers of ICF in the North American and European business communities. But in 2009, when the downturn happened and we saw a recession take hold, that market then shrunk down to 10 different primary manufacturers. And that's essentially what you see today. Is there's about 10 different major manufacturers of ICF in the market today. But what we have seen since 2009, and especially now in 2020, with what's been happening with the wood industry and the price of wood this year, we've seen unprecedented market growth. And one of those markets that we're going to be talking about is educational facilities. So let's look at envelope performance using ICF. So ICF's construction process sets it apart from other types of building systems. Now, I have to stop here for a second, and I have to emphasize, a lot of people, when they want to compare what ICF is to other types of building shell exterior types of construction, you have to understand that ICF is a system. It is not just simply a concrete block. It is not simply a wood framing. It's not simply metal framing. It is a system, and there's many things involved in that system. So here's a list of some of those things that are in that system. So you have a formwork that stays in place. If you're familiar with how typical cast in place walls are done, you have a form that gets erected. You have rebar that gets installed on one side of that form, and then the other side of that form gets put in place, and then the concrete is poured. Well, in the case of ICF, that formwork actually stays in place because that formwork actually has multiple applications that it has to be used for. So that formwork, which is actually expanded polystyrene, acts as a thermal barrier. And you don't just have it on one side, you've got it on two sides because it acts as the two sides of that concrete form. It's also a vapor barrier and a moisture barrier. It's actually a class 2 vapor barrier. I get this question a lot from architects and contractors about, do you not have to have a vapor barrier on the outside of this before you put up brick or before you put up any other sort of finish on the outside of ICF? The truth is that the only place that we recommend that you really have to have some sort of rain screen or vapor barriers when you're going, or waterproofing, excuse me, is when you're going below grade. Because this is a class 2 vapor barrier. You do not have to put an exterior wrap on the outside or vapor barrier on the outside of ICF, because the EPS and the way that those forms lock together, and then with a monolithic pour of concrete in the center, you do not have moisture infiltration that comes into your inner conditioned environment. It's also a fire barrier. We'll talk a little bit more about that in a second, but it's a minimum of a 2-hour fire barrier. It's also a very excellent sound barrier. STC ratings begin at a minimum of 50 and continue to climb from there. Also, it's a furred substrate. We'll look at this here in a second as well, but you have the webs that actually hold the two sides of the forms together. And those HDPE, or high density polyethylene webs, actually, they're really kind of the unsung hero of an ICF block, because they hold the form together. They actually become your furring system, and they become the place that you lock your rebar in, or your interior reinforcing inside of that concrete wall. So I just talked about that the webs become the attachment furring system, so you don't have to fur these walls out. In other words, you don't have to put hat channel or some sort of system on the outside of it to attach either sheetrock on the inside or a finish on the inside or exterior finishes. But when it's done, you have a reinforced concrete structure that is poured in the center of this with a super insulated shell on the outside that already has an attachment system associated with it. So once your ICF contractor walks off the job and he's done with his part of the contract, you have your attachment system, you have your insulation system, you have your structure in place, and there's many, many masters that are served from being able to use ICF for your exterior wall shell. So what are insulated concrete forms? So they are a cast in place concrete wall poured inside of an EPS form that remains in place. Your cavity width, which is the concrete wall core, usually varies from 4 inches to 12 inches. Now that is the size that most of your manufacturers manufacture their block already assembled. You can get larger cast in place walls. In other words, if you have to go to, for whatever reason, structural engineer wants a 16-inch wall, if he wants an 18-inch wall, or if you even have to go thicker than that. Just about all the manufacturers produce a form that will go that thickness of wall. But typically, anytime you get above a 12-inch thick wall, it's usually a form that has to be put together on site. It does not come pre-assembled. But it varies from 4 inches to 12 inches, and the EPS insulation is usually 2.5 to 3 inches in thickness. Just depends on the manufacturer that you choose of ICF, but it's usually a minimum of 2.5 inches. And as I mentioned before, the HDPE webs, the high density polyethylene webs, provide form, structure, and rebar placement and finish attachment. As you can see in the diagram on the right-hand side of your screen, you've got the concrete in the center, you've got your steel reinforcement, your rebar, which you would typically see in any cast in place wall. You have the layers of insulation on both sides of the wall, not just one side, but on both sides of the wall, which equates for having your air and vapor barrier on both sides of that wall as well. And then you've got your furring strips, which are the vertical black strips that you see there. Now, the way that this differs in a lot of ways in attachment point from, say, a framing type situation or a sheathing type of structural situation. With ICF, you have an attachment point vertically every 6 to 8 inches on center. Typically, in most other types of methods of construction, you're having to try to hit, especially if it's something of any size and weight, you're trying to attach to a stud or trying to attach to some sort of structural member. And that's usually at the most 16 inches on center. Sometimes it's upwards of 24 inches, just depending on what your framing is or what the structural system is. With ICF, you have an attachment point for any sort of finish, and it's usually every 6 to 8 inches on center. Now for my, I'm just going to talk to my architects and my contractors for a second. So forgive me for those of you who are not necessarily in the industry, but I just want to give you a quick little wall section cut through of how an ICF wall is put together. You can see a wall section detail is on the right-hand side of your screen, showing the attachment of finishes. You've got a 1/2-inch gypboard that is able to attach directly to the ICF. It shows the cut through of the ICF block, and it shows the concrete being poured in the center. You can see the webs become, the HDPE webs become the receivers for the steel reinforcing. And then when you get to the outside, you can put your masonry ties directly to the furring strips. And I probably neglected to mention that these furring strips are rated for up to a 250-pound pull. That is actually more than what a wood stud is rated for in its actual pull force and being pulled out. So you can actually attach your masonry clips anywhere as long as you're hitting on that web. A lot of people ask, well, how do you know that you're hitting on it? all the manufacturers that make ICF will tell you they've got a panel pattern that's on the outside of their EPS panels, that it's either, sometimes it's their name, sometimes it's a helix pattern. It just depends on the different types of finishes that you're doing. But there's a pattern that shows you exactly where the furring is, so that you know exactly what you're attaching to. And as you see in the red type that's there on the screen, matching ICF block modules, usually most of the ICF block is set up on an 8-inch type of module. That way it matches mostly with your masonry setup with an 8-inch model, having it 8 inches spaced in each direction. Not every ICF block is that way, but to be honest with you, it's really not a concern whether it is on masonry coursing or not, because once that wall is set up and in place, you've got your attachment points and you can put any finish on it, and it really is not a problem as you would probably experience with using concrete block or some sort of masonry unit. As you can see down at the bottom, that is just kind of an axon, or just kind of a perspective look on an ICF block. Most of your ICF block is usually either 4 inches long or 4 feet long or 8 feet long. That's your typical ICF block. And as you'll see in the next diagram we're going to pull up, this is the construction steps that you typically would go into when you are putting together an ICF wall. So number one diagram actually shows you that this is the stacking of the wall. So you typically would have a footing that would be in place. When that footing is in place and in the corners of the building are pinned out, you would start stacking the block. As you stack each course of the block, you go all the way around and provide your horizontal rebar. Typically, you'll already have vertical rebar coming out of the footing that you'll attach to, but you'll have horizontal rebar that will lock into those webs that we've talked about, that are kind of the multifunction part of the ICF block. As you go to reinforcing, which is what number 2 shows, and you're attaching all that rebar, by the time you get up to maybe 4 to 5 courses of ICF block, you're going to wind up attaching a bracing system that is also a multifunction device in itself. This bracing system will attach right to the point that you have a furring strip, and then as you can see, it has a diagonal brace that goes back, and it'll either be attached at the grade or it'll be attached at your slab. It just depends on what you are bracing back to. But as you can see, if you look closely into the middle of that picture, it shows a little turnbuckle. Now that turnbuckle is used to straighten that wall up and to keep it plumb, because as we go to diagram number 4, figure number 4, as the concrete is poured and placed down in the center of that wall, that's a lot of force that's coming out of that chute from that snorkel truck. And that's typically how you would place concrete in an ICF wall. And so what most of your ICF installers will do is they will do what's called a lift approach to placing the concrete. So they will put a 4-foot lift inside the wall. In other words, they will pour up to 4 feet of concrete inside a wall after they have stacked the wall to the height of, say, a floor. Typically, most of your contractors are going to do no more than 15 to 16 foot at a time when they're pouring these walls, and that's your typical floor height anyway. So it really kind of works out. But they'll pour 4 foot at a time. Once they have poured 4 foot of concrete inside the wall, they will quickly go around in the same day and in the same pour time. They'll check each one of these levels, each one of these braces, to make sure that the wall has stayed plumb, that the wall has stayed true and in place during the placement of the concrete. And as long as everything checks out, then they will turn around and they will place another 4 foot lift of concrete down in the wall. And they will continue and repeat this process until they get to the height that they want to achieve. Next, you have the installation of electrical and rough ends for plumbing. It's because your EPS foam is typically 2.5 to 2 5/8 inches thick. That typically coincides with the thickness and the depth of a junction box. So all it really takes is to have the ability to cut the foam, whether it's with you could use a drywall knife, you can use an electric saw, whatever you choose to use to cut out for your junction boxes. And if you're not up against, because of where your junction box is having to fall, if you're not up against a furring strip, and as you can see in this one particular picture, there's a helix pattern there, and that actually identifies where the furring strip is. If you're not up against a furring strip, all you have to do is put a Tapcon or concrete screw through the back of the junction box and then attach it to the actual monolithic concrete pour that is the core of the structure of the wall. So as long as your conduit is not larger than 2.5 to 2 5/8 inches in thickness, which is, typically you wouldn't see that, but you will have some stack piping from time to time that could be 2.5 to 2 5/8 inch or even larger. As long as it's not any larger than that, it will recess back in the foam. And typically what most of your ICF installers will do is they'll ask electricians or they'll ask plumbers to come back and just apply some foam over their conduit or over their Romex wire to make sure that they've gotten the rough end in place correctly and they haven't sacrificed any of the insulating value on the wall. And as you can see on the diagram number 6, figure number 6, any sort of finish attachment, any sort of finish that you would do on a regular type of structure, or a typical type of frame construction, you can do with ICF. Whether it is hardy board, whether it is masonry units, they will work just perfectly fine with ICF. And if you're someone that does and specifies a lot of synthetic stucco, there's actually a cost savings by using ICF because you don't have to put the base layer of foam down because you've already got a layer of foam there for the base layer. So the only foam that you really have to apply is any additional foam for any sort of architectural detail, whether it's a window wrap or a door frame or a door header. And as long as you back wrap and bed those attachment points, then you should be fine, and it winds up saving you money because you're not having to add the extra layer of foam on there. So just to give you an idea, just some of the standard shapes that most of your manufacturers are going to have. There's a straight block, which I described before, that's either 4 feet or 8 feet in length. You have a corner block, 90-degree corner, typical 90-degree corner. Most of your manufacturers will actually make a 45-degree corner. There are some manufacturers that will do 30, 15, 60-degree corners, and some that will even do custom corners for you. But most of your ICF installers who've been in the industry for a little bit, they know how to cut a block and create a custom corner in case you have an angle that does not fall in one of those typical degrees that you're used to seeing for a corner of a building. The next one is kind of a money saving, kind of a unique feature of ICF, and that you have an ICF brick ledge. For those of you who have dealt with having to install and detail brick or masonry units going on an exterior building, such as stone or some sort of, cast block, this is a real money saver because instead of having to take your exterior masonry finishes down to the top of your footing, you have the ability to start the support for your masonry just a few inches below your finished grade, and then start from there and take your masonry finishes on up. So you're not paying for masonry, whether it's stone or brick, you're not paying for that to be installed below grade where it can't be seen. And it winds up being a cost savings in a lot of cases, especially if you have a site that's sloping or a walkout basement type of application, winds up saving a lot of money. So this is something that's very unique, but also is used a lot and used widely, and has gained a lot of attention for ICF installations. Last but not least, we see a radius block. Most manufacturers make a radius block that's either on 12-inch or 24-inch radiuses. A lot of the manufacturers also, if you tell them the type of radius and the size of radius you want, they will make you a custom block if you just tell them what the radius has to be. So there's a whole different number of different applications for using ICF for any sort of design application that you can think of. So let's look at some wall section cost comparison. I won't dive too deeply into the details here, but I'm sure a lot of you can look at this wall section detail and realize that this is probably a section most of you have drawn several times over the years. Standard CMU wall, typically, even though I don't show it in the detail there, would have a hat channel with a furred sheetrock on the interior. On the exterior, you've got your continuous layer of insulation, which is pretty much required now by the Model Energy Code. You have your airspace, and then you have a masonry type of detail, whether it's stone, brick, whichever on the outside. So looking at cost comparisons, when you look at a CMU with a brick veneer, right now in 2020, we're seeing those numbers somewhere around $40.38 a square foot in the North and South Carolina markets. With ICF, as you can see, there's a significant difference in the cost in that the ICF wall becomes the structure, the ICF wall has the insulation, and the only thing that you're worried about doing is putting the brick in. As you can see, we detailed out showing the actual masonry shelf that the brick would actually sit on. So the cost per square foot difference, 17%. And I can go ahead and tell you now, because I am one of the people who is working with the Concrete Design Center, which I'll talk about a little bit more here in a little bit, when it comes to wood framing, we're actually seeing some of those numbers climb even above that. So the arguments that we've heard in the past that concrete walls or insulated concrete walls are too expensive have pretty much eroded away, because we're very competitive with first cost, but we're also very competitive over long-term maintenance cost for a building. So concrete buildings, they are safer and they're quieter. We talked a little bit before about fire rated walls, but the minimum fire rating you're going to get is a 2-hour wall for a 4-inch core. Whenever you hear someone refer to an ICF and they say it's a 4 or 6 or an 8-inch wall, it's referring to the thickness of the core. So if you have a 4-inch core wall, it's going to be a minimum of a 2-hour rating. If you have a 6-inch wall, it's going to be 3 hours. If you have a 4-inch wall, it's going to be 8 hours, and then your ratings are just going to go up from there. But typically 3 and 4 hour walls are not unheard of and are very common using ICF. Fire rated floors, if you use an ICF floor system, and there is an ICF floor system, we won't talk about it a lot today, but you can use, there's ICF floor systems where you have a form that concrete is poured on top of. You will get a rating of 2 to 3 hours out of it. It is high impact resistance. This wall actually will resist a minimum of a 200 mile an hour wind and impact. So, which is very important, especially when you're trying to design to ICC 500 requirements. And most notably that we have seen is that sound transmission is almost nil when it comes to using ICF to block sound. You get a minimum of 50 STC out of an ICF wall, and depending on what sort of finish and treatment that you do to that wall, you'll just see that number go up and climb in its resistance. So what we hear a lot, especially in the multifamily industry, is that sound is one of the #1 reasons why people do not stay in an apartment or in a condo or in a multifamily type situation. If you take that sound infiltration out of the equation and eliminate the sound infiltrating into one space from another, then you've automatically increased the occupancy of that facility, which means better occupancy ratings for the owner. High performance envelope. So a lot of people ask, what's the standard rating of an ICF wall? So you're going to get a minimum static. And that's, in other words, if you just added up the R factor or the resistance factor of each one of the materials used in an ICF wall, you're going to get a minimum of an R24. But when you consider the performance factor of an ICF wall, which means how thermal mass plays into the slowing down of the heating up and the cooling in between the two different environments. In other words, interior environment to exterior environment. These walls typically perform as an R30 plus wall. You have a reduced air infiltration and air exchanges with solid cast in place concrete walls. It's encased in the 2 layers of EPS, as we've talked about, and all penetrations wind up getting sealed. And this equates to a half of an air change per hour, which is extremely, extremely efficient. So, a summary of our code advantages. So ICF provides safety and resiliency. And when we're talking about our children and we're talking about the educators that are taking care of them and teaching them during the day, safety is key. So we're also talking about excellent R values. When you're talking about the Model Energy Code, the IECC code is very energy code compliant, has excellent fire resistance, minimum 2 hours, we discussed, has excellent noise attenuation, which plays into your environmental quality. And if you're even looking at a facility that has to be living building challenge compliant, being able to control noise is also very important. And then high wind load resistance. We've talked about this, ICC 500. This is very much a large component of ICC 500 and being able to provide a structure that can resist inclement weather that has high wind rating. So it's very safe. But then there's also the reduced operating, maintenance, and insurance costs. We'll dive into this a little bit more in the case studies that we're about to look at, but we have seen reduced operating costs, especially from energy savings that can exceed 30 to 40%. These buildings are much cheaper to maintain than other sorts of framed buildings. And the insurance industry has recognized that an ICF building usually can help them achieve a cost of insurance that we've actually seen some numbers that have been coming in 50% plus in savings for builders risk, owners, and liability insurance on a facility. So a real quick summary of ICF construction advantages. It's faster installation. Remember, it's a system versus a unit, so that helps to expedite any trades that you'd have on the job. It's also reduced construction schedules. Typically, we see ICF walls when ICF is used as an exterior shell. It can help reduce the overall construction schedule 15 to 20%. We also see reduced worker fatigue. There's less industry. Remember, you're stacking block that's made out of foam, and then you're pouring that block with concrete. So you're not trying to get masonry units into place. You're not trying to get large steel member or wood members into place. You're stacking it up a course at a time and then pouring it once you get to the height that you need it to be. You have minimal heavy equipment and machinery on a job. Typically, the only heavy machinery that you'll see in an ICF install will be something like a lift or a lull that will help haul the block up into place on the scaffolding or on the bracing for the next layer to be going up. You also have very efficient design. Most contractors will tell you that material waste can be a big factor on a job. Well, most material waste factors for contractors, whether it's block or wood framing or steel, is usually somewhere between 5 and 10%. Most of your ICF contractors have a material waste factor that's somewhere around 3% or less. But you have superior weather protection. So this is very important when you're pouring, especially in colder temperatures, as we've all kind of been experiencing here lately. It's gotten a little chilly. We're starting to get into the winter months. And the last thing you want to see is somebody trying to pour a cast in place wall when the temperature is below freezing. Well, the beauty of ICF is that the insulation protects the concrete during these hot and cold temperature extremes. And with that, you're helping to control the two things that concrete needs to achieve superior hardness and curing, and that is you're controlling the heat loss and you're controlling the moisture loss. If you control those two, then you wind up getting a wall that at least it meets or exceeds the PSI or the strength of the wall of the concrete that you've poured in it. Typically, especially if you're pouring when it's below freezing, and you can pour walls when it's below freezing with ICF, all you have to do when you get up to the height of the top of that wall is provide a thermal blanket that sits on top of it temporarily while that wall is curing it in place. Again, I want to emphasize this is a system versus a unit. So system versus unit installation, you have EPS installation forms, you have the HDPE webs and furring, and then you have a concrete core and thermal mass. And then I would be remiss if I didn't point out that with LEED points, and we're going to talk about this real quickly, ICF contributes over 60 direct and indirect points to LEED certification. There is not a system out there, and I challenge anyone to show me a system that can achieve as many points in LEED as quickly as ICF does. So let's talk about that for just a second. So LEED optimization. LEED can be achieved through ICFs very easily through the energy savings, through life cycle assessments, through your EPDs or your environmental product declarations, noise reduction, IAQs, innovation, and resilience. So what does all that mean? So with your direct points for LEED, you can satisfy the energy and atmospheric prerequisite right off the bat. You can also get a minimum of 10 points for the energy and atmosphere direct point requirement. You also can get a minimum 6 points for material and resources, because concrete is typically a material that's very local. It's not something that's being shipped in. So you're able to achieve those points, the direct points, by using ICF. So let's talk about the indirect points real quick. It's sustainable site credits. You get 2 points. Energy and atmosphere, 3 points. Material and resources, you get 2 points. And then you meet the prerequisite for indoor environmental quality, and you get a minimum 6 points for that indoor environmental quality. Now, we've rushed through that very quickly. If any of you want more of a detailed explanation of how these points are achieved, please feel free to email me after this, and I'll be glad to send you a form that shows you where all these points can be gained at. So let's look at some case studies real quickly before we do some questions. Warren County Public School Systems. This is Richardsville Elementary. Architect was Sherman Carter Barnhart. This is the nation's first net zero school. A little less than 73,000 square feet, 550 students. Had an ICF exterior envelope. They used geothermal HVAC heat pumps. Had clerestory day lighting throughout the facility. They also had a photovoltaic solar array mounted on the roof and in the parking lot. Now, when we talk about energy efficiency, especially when it comes to schools, we use a term called EUI. Now, EUI is the energy usage and intensity. Most of your schools in a climate 4 zone, or most facilities in a climate 4 zone, are going to perform at about a 73 EUI. ASHRAE likes to see that number standard at 65, and they even say that for you to have that a facility to be ASHRAE certified, it needs to be at a 45. Richardsville was built over 10 years ago, or right at 10 years ago, excuse me, and it performed it right off the bat at 18.9 EUI, or 1,000 BTUs per square foot per year. That is the rating for an EUI. That was in its first year. Now, they have a solar array that's generating power as well. So in the first full year of operation, which was 2012, they received a rebate check back from the local utility for $37,227. Now, that is what they generated in power, and that's above and beyond what they used in power. So this facility actually generates more energy than it uses. Now, how are they using that money? What happens with that money? In this specific case at Richardsville, they're actually taking those funds and applying those to a teacher's salary, and they're able actually to add additional staff at the facilities that are doing this in Warren County. So let's look a little bit deeper at these numbers that we just talked about. You can see the comparison there. 65 EUI is what ASHRAE likes to see a typical school be at. If it's going to be a ASHRAE certified school, they want it to be at 45. Richardsville actually operates now somewhere around a 17, I believe. I think that maybe that number's went up a little bit. I think it may be at an 18 now because they've made some equipment changes there at the school. But the reason why it's at 17 now, even though I told you it was 18.9 when it started out, when the school was originally built, it was all the lighting was compact fluorescent. Well, they made a change a few years into the school being open and changed it all to LED, and that dropped the EUI even further down to 17. The table that you see on the right-hand side of your screen is just an estimate of the energy savings per year at Richardsville. First year of operation, their energy savings was almost $63,000. As you can see, those numbers have continued to go up, and their estimate is that by the time they reach year 15, they will have seen over $1 million in savings just at this one facility alone because of the way that it's been built and the systems that it has employed. So here's another one that's maybe a little bit closer to you guys. This is up in Arlington County, Discovery Elementary School, right outside of Washington, D.C. Much larger school, almost 98,000 square feet. It is a net positive energy school. It saves over $100,000 a year in utility costs, and it performs at an incredible 16 EUI, still the best performing school in the nation right now. Multiple awards, as you can see, AIA, A4LE, also has an ICF exterior envelope. It has a solar photovoltaic array and a solar water heater mounted on the roof that helps with reducing those energy costs. Geothermal HVAC, and also has 100% LED lighting throughout. These are two of our most recent schools. There's only one picture because they're actually identical schools that were built in the Baltimore, Maryland area. Baltimore City Schools, these are Hallbird Elementary and Graceland Middle School. Both schools are just a little bit more than 94,000 square feet, have a capacity of 600 students plus. A little bit more expensive because of the area that they're being built in, 34 million or 360 square foot. They just opened this year. So this was the first year of operation. So their projected EUI is to be about 20. We don't have any data yet, or at least a year's worth of data yet to show how they're performing. But both of these schools have been applied as LEED Platinum. That's how they're tracking right now. Also, some of the same features that you've seen on some of the others: ICF exteriors, solar photovoltaic array, geothermal heat pumps, and 100% LED lighting. So some final thoughts for you before we get some Q&A here. Resilient structures are an important part of our communities. Storm-resistant exterior shells that are ICC 500 compliant are quickly becoming the standard for educational facilities. High performance envelopes improve that energy efficiency. ICF walls result in resilient, cost-effective structures. Now, I need to say this. Could you achieve some of the R factor, and could you achieve some of the results that we have seen in these schools if you did an exterior shell out of something other than ICF? I think the answer is yes, you could. But at what cost and at what sort of effort would you have to go to? These are a 9-in-1 efficiency in the system. They're thermal and air moisture barriers, fire and sound. There's so many advantages to using ICF. That's why you see the schools that have achieved net zero are using either insulated concrete or tilt-up concrete as an exterior barrier on the outside of these schools. Quality control and safety. One of the things that can't be ignored, and would be remiss if I didn't mention it, is that when you're using a reduced number of trades working on a high performance wall, you have higher quality. So the less people you have touching that wall, the less people you have installing that wall, by the time they're done, the higher the quality is going to be on that wall. So that's where the time savings come from. That's where your quality and performance comes from. And again, on the quality control and safety, we also experience year-long construction. As I said, we don't have to stop for when the weather turns bad, and the temperatures drop. We can continue to build all year long, which winds up saving in time and money in the cost of the construction. So your ICF walls result in a very high rate of return, rate of investment for the owners. Reduced construction schedules equal getting to operations faster. Reduced utility and insurance costs, or more money back in the pocket of the owner of these facilities, and you have reduced maintenance costs on these facilities as well. They're safe and they're healthy. The environmental comfort promotes better learning environments for all students and the educators that are inside these buildings. And you're being a better steward of the community's resources around you. So savings can be diverted to other needs, just like in the case of Richardsville, where they're actually using the utility savings to provide an additional teaching position in the school. And they become safe community spaces where storm shelters can be established that are ICC 500 compliant. That way they have the ability to set up base of operations in the case of inclement weather and disaster events. I'd be remiss if I didn't talk about our concrete design center that we have in our MCA through the Build with Strength program. We can take any facility that you have designed, even if it's in schematic design, and we can give you a cost comparison and a detailed comparison of what it would be like to build out of ICF. You can go to buildwithstrength.com and you'll see this page that you will fill out the information. You also can contact me. You'll have my contact information here in a minute, or Jessica Palmer, who's with the Carolina Ready Mix Concrete Association. Let us know that you have a facility that you would like to see a cost comparison done on, and we'll be glad to do that for you. And most importantly, and most notably to a lot of people, we do this as a service to the builder and design community around us. This is this is no cost to you. We take care of that. That's part of the service that we provide, because we want to see more people building and using ICF and insulated concrete walls for their exterior structures. Talking about some of those resources from NRMCA and CRMCA, you have design assistance that we would provide. You have lunch and learns, which we do all the time for people. Online webinars like we're doing today, case studies that can be provided, personalized AIA approved educational opportunities, and seminars and association partnerships. Just to give you an idea of how we cover the country, again, I'm Frank, that you can see there in the orange section, that's the area of country that I cover. We have a representative that covers each area, as you can see, each region. So no matter where you're going to be building at, no matter where your project is at, we have somebody that can help you address the needs of your facility. And again, here's our contact information. I'm with the National Ready Mix. Jessica's with Carolina Ready Mix. Please feel free to copy down the phone number and email. Feel free to reach out, contact us at any time. So let's look at some questions that have come up here. First one was, would the slides be made available in PDF format after the class? Yes, we will be providing this, but you'll also be able to watch this video again. They will post this video on the A4LE website so that you have the ability to see it. Can you run electrical and cabling services on the interior side? I think we kind of addressed that, but just to reiterate, yes, you can. You can. A lot of people ask, well, how do you do this? If you have a hot knife or a spade bit that can be used in a either like a rotozip tool or even a router. I've even seen an electrician that works a lot with ICF that uses an electric chainsaw, and he has a guard set on it, so it will only groove out to a certain depth, the depth that he needs to run his conduit. So it's very, very easy to run your interior rough ends on the interior side of these walls. Says, would number 5 come before number 4 in the sequence of construction events? And I think you're referring back to in that you would put the electrical or the rough ends in before the concrete. And typically, no, we'll put the concrete in first because you want the concrete there to be structured to hold that wall in place. And then you can put all your interior rough ends in after the fact. So that's typically that's why it's sequenced the way that it is. And I don't see any more at this time. If anybody has any others, feel free to offer them in. We finished a few minutes early. So I do want to say thank you again, not only to the North Carolina and South Carolina chapters of A4LE, but also the A4LE themselves, also to the Carolina Ready Mix Concrete Association. I appreciate them being a sponsor and a great partner in the Carolinas for promoting these sort of structures. If anybody has any questions, again, please feel free to email them to us. You also can go to the websites that you see there below on the screen and access some of the information you've seen today as well. But I thank you for your time. I thank you for listening with us today, and hope to see and hear from more of you again in the near future, because we would love to help you with building schools more effectively and efficiently using the ICF. All right. Thank you again, and look forward to talking to you. Thanks for being here.